Hello class, welcome to lecture 19. So today we're talking about confidence intervals again, but for sample means instead of proportions. So last time we did confidence intervals, but it was all about proportions. So the idea was to estimate proportions using a sample proportion. So now we're going to do a very similar thing, but we're going to estimate a mean using a sample mean. And so again, there's going to be some theory that will sort of make it seem more complicated than it is when it comes to doing problems, but we do have to go through it. Okay, but this is the big picture idea of these types of problems that we'll be looking at. So just keep that in mind even as you're working through the details. All right, so this time I'll describe the process for doing the problems before I go through the theory. And you should think about it in comparison to what we just did with confidence intervals. So we're going to get, first step is we're going to get a sample mean, which is going to be called little x bar. So that's sort of like getting a sample proportion, aka this is a point estimate for this type of problem. And then we need eventually to make the confidence interval, which means we need to make a margin of error, which means we need a standard deviation. So we're going to get a sample standard deviation. And so it's a standard deviation of a bunch of data. So it's going to be calculated just sort of very similar to how we calculated standard deviation a very long time ago, but it's going to be called little s. And we'll see that it's a little bit different than what we're used to doing. So just keep that in mind. The key is that it's a sample standard deviation, and that's why it's different from what we did before. Okay, so then after that, we're going to obtain something like a critical value. So that is in the proportion problems, the critical value is what tells you how wide the confidence interval is, like how many standard deviations to go out. But for means, we actually can't use z-scores. And so we're not going to have a critical value that's a z-score. We're going to have something called a t-value. So don't worry about what that is yet, but it's called a t-value. And it's just like a critical value, but for something else. And then after we had the critical value and the standard deviation, we multiplied them together to get a margin of error. That's going to be the same because that's just how wide the confidence interval actually is. But now instead of a critical value, it's this t-value that we multiply to the standard deviation. But it's not just times the standard deviation, because we actually want the standard deviation of the distribution, which means we have to do s over the square root of n, which may look familiar to you. It looks very much like this formula we used a long time ago for the standard deviation of the sampling distribution of the sample mean. Don't worry about all that for now. The point is you have to multiply to get a margin of error. Then you get the confidence interval just by adding and subtracting that amount. So you just add margin of error to your sample mean, and that tells you the right side of the confidence interval. And then you subtract it to get the left side. So it's a very similar process. What's different is we're talking about some other normal distribution type thing that involves t-values instead of z-scores. Okay, so that's what we're going to dive into now before we do a real example, just to get the idea of the theory down. So here's the theory. We're not going to go into it as deep as we did for the other stuff, but so you're just going to sort of have to believe some things I say without justification. So there's something called a t-distribution. And it's very similar to a normal distribution. It's so similar that you basically can't distinguish them. So I'll draw a t-distribution, and it'll look just like a normal distribution. That's because they are very similar. But what's different is that t-scores instead of z-scores tell you the area, which we would then think of as probability. So then the process that I described up here creates a interval based on this distribution. Instead of the normal distribution. So that's cool, I guess, but we don't really know what this distribution is. All I know is that it looks very similar to a normal distribution so far. But we'll get into details in a second. So then the point is that t-values will correspond to t-scores, just like critical values corresponded to z-scores, where they're based on the amount of area that you want, and that's called your confidence level. So the amount of area based on confidence levels. So we're still going to always be looking at 90%, 95%, or 99% confidence levels. So we're going to make confidence intervals based on these numbers. And that just is corresponding to another area in the middle, but now in the middle of this other distribution. And then that's going to correspond to some t-score. So you're going to say t equals something or something else if it's 95, or something else if it's 99. But what's different is that this t-value doesn't just depend on these percentages. It also depends on the sample size. So what's different is t depends. So for z-scores and critical values, the z-score was always the same for each percentage. So like 95% confidence always goes with z equals, I think it was 1.96. But the t-score for 95% confidence will change depending on the sample size. Okay, so what's different is t depends on sample size, whereas critical value instead of t-value. So the z-score only depends on confidence level. And the reason behind that is very technical, but what's going on is I sort of lied. There's not just a single t-distribution. So depending on your sample size, you get a different distribution. So you get a different t-distribution depending on the sample size. And the bigger the sample, the more it looks like a normal distribution. So that's the reason that your t-score depends on your sample size. It's because your distribution, first of all, depends on your sample size. Whereas your normal distribution, your z-score distribution doesn't depend on sample size. It's always the same. Okay, so again, in practice, this theory is not gonna get in the way too much. So let's jump into an example now. So here's the idea. So you need a sample, and then you need a sample mean. So here's some data. So given the following, so this is 2011 Ford Focus type of car, miles per gallon samples. So took a bunch of Ford Focuses and got their MPG, and this is what you found that they were. So I'm gonna write them down. I should have written them down ahead of time and popped them in, but that's okay. Okay, so here are some, whoops. 2, 41.3, 38.8, 40.9, 34.1, 38.2, almost done, one more column. Okay. So these are the miles per gallon of 16 for 2011 Ford Focusi. So we're going to construct a 99% confidence interval of the mean miles per gallon of the 2011 Ford Focus. So again, here's the idea. If I wanted the actual mean of all 2011 Ford Focuses, I would have to know the miles per gallon of all of them and find the mean of that. That would be the actual mean of the population. But instead, I don't know that. So I have this sample of 16 of the Ford Focuses, and I'm going to calculate their mean instead and use that to estimate the actual mean. That's the big picture idea that's going on when you construct a confidence interval. Okay, but let's go through and do it. So first thing we need is the sample mean. That's just the usual mean. So remember how to do that. You just add up all the numbers, then divide by how many there are. In this case, there's 16. So you can use a calculator to do that if you want to check your process, but you'll end up with 36.8. So the process is more important than the specific individual answers each time. That's the idea. You should know how to do that. Okay, so that's our point estimate for this type of problem. This is our sample mean that we're going to construct a confidence interval around. And now we need the sample standard deviation. So I warned you at the beginning that this is a little bit different than the regular standard deviation. So the standard deviation that we learned how to calculate a long time ago was for populations, but it's actually a little bit different for samples. So if you use a calculator, you need to Google sample standard deviation calculator. And you'll end up with 2.92. So the process by which you calculate is you do the same thing as you used to do, except you divide by n minus 1 instead of n. So we calculate this by dividing by n minus 1 instead of n in the old process that we learned a long time ago, where you take your mean, you subtract each number minus the mean. I'm not going to do it right here, but you do that for all of these. Then you square everything. Then you average those, and then you square root at the very end. When you average those, that's where you change n to n minus 1. So you're going to divide by 15 instead of 16 in that big process. So notice here, you're still dividing by 16 when you get the mean, but here, to get this in that long process, you'll be dividing by, instead of 16, 16 minus 1, which is 15 in that process. But I don't recommend calculating standard deviation by hand anyway. So really, you should just Google, or if you have a fancy calculator, it'll do this for you, sample standard deviation calculator. And then you can just type in the data and it'll calculate it for you. And you'll know it's it because it'll call it little s. Okay, so in any case, that you're not going to do by hand anyway, so don't worry too much. Okay, now we get the t-value. I don't know why I underlined it. Okay, so we're going to get the t-value. So you need two things to find the t-value. So I hinted at this in the theory. You need something to do with the confidence level, but for some reason, stats people like to have extraneous names, so they call it the alpha level, and it's dependent on the confidence level, but it's not the same as the confidence level. You might also hear it as significance level. And all it is 1 minus your area that the problem is stating. Oh, this is a 99% confidence level. So I'm going to not use 0.95, I'm going to use 0.99. But the rest of the question, I used 0.95, so that's going to mess up my later calculations. So I'm going to cheat. I'm going to go back and I'm going to change the question. Let's construct a 95% confidence interval instead, so that all my calculations I preemptively did work. Okay, so that means that this will be 1 minus 0.95. So see, your alpha level is just based on that initial question. Okay, so it's 1 minus that is 0.05. You could just think about it as what it really is just the leftover area on the t-distribution. So the idea is you have your t-scores, t and negative t. This is the t-score you're looking for. And your confidence level corresponds to this amount of area, which in this case would be 0.95. And then the total outer area, the blue area, that's going to add up to 0.05. The leftover, and that's really what alpha is. in these problems. Okay, so that's what we need. And then, so this t-score is what the calculator is really going to be producing. Well, it's going to give you the positive one. It's going to give you this one. Okay, and then the other thing you need is something called the degrees of freedom. Another extraneous term that stats people have created, or they just call it DF very often. And all it is the sample size minus 1. Why do they have to name it something? I don't know. You just do the sample size minus 1. But it has a fancy name. So in this case, the sample was 16. There were 16 things in that initial sample that I wrote down. So it's 15. It's the same number that you're going to be using if you did calculate the standard deviation by hand. Okay, so then you take those things and you just plug them into a specific calculator that I will link to on Moodle. So you just have to plug in the alpha level and degrees of freedom into a very fancy name, a two-tailed t-value calculator. So again, I'll link to this on Moodle, calculator. And if you do that, it'll tell you t equals 2.131. Yeah, okay, so that's it. So I'll leave more instructions on Moodle, but the reason it's called two-tail is because later we'll do something else. But here on this distribution is because the total area of both sides is 0.05. But if we were just looking at only one side for some reason, it would be a little different. Okay. Then to get our margin of error, and now we've done all the hard work, you just take your t-value, multiply by your standard deviation divided by the square root of n, which in this case was 16. So this is just S, this is just the sample size, and this is just your t-value. Okay, if you do that, you'll get 1.556 in this situation. And that's how wide your confidence interval will be. So the last step is just to take your sample mean and add the margin of error to get the right side of the confidence interval. So that was 36.8 plus this number I just got. That'll get you to 38.356. And then you do the same thing, but you subtract. So that'll get you 36.8 minus this number, which will be 35.244. Then we just have to answer this in context in a very statistician-y way that people like to say. So here's the actual answer to the question once you've done all this work. We are 95%, because that's what I changed it to, instead of 99. We are 95% confident that the mean MPG of the 2011 Ford Focus, so you see the idea was we're trying to figure out how to estimate the actual mean so that we're 95% confident that that actual mean is between these two numbers. It's in this interval. It's 35.244 and 38.356. So then again, in other examples, what's going to change is I'm going to change this number. That's basically what's going to be different. And then you're just going to use that calculator to get different t-values. Okay, so that's it for today. So we'll have lots more examples on the lecture problems, but see you next time.